Hi, everybody. Today I'm going to introduce to you the equation for the correlation and its calculation. We'll actually practice calculating it next time. In this lesson, I'm just going to explain to you what the equation looks like, what it does conceptually. Okay, so once again, we're getting familiar with a correlation. We're starting to understand how to interpret it. We're starting to understand how not to misinterpret it as well, and things like that. So, as I said, we're not going to jump into the calculation today, but I'm going to explain and describe to you what the equation itself does so that we can understand in concept better what the correlation itself is. Also, just like we practice with the standard deviation, there are two equations that we can use. One of them is the actual concept of the correlation. I'm going to explain that one to you. But in the actual practice of calculating, there's a simpler one that uses fewer steps. And so that's the one that we'll use for simplicity's sake, just to save time. So I will now show you the equation that actually does what the correlation intends to. And then when we practice, we'll actually use the mathematically equivalent version. But that'll also be at the end of the video. I can show you. Okay, here's the equation for Pearson's R. Pearson's R is, of course, the typical correlation that we're talking about. There are some special correlations out there depending on the kinds of variables that you're using. For example, if you have a binary variable, a dichotomous variable, same thing. There are some other things to do here. But this is the equation that we're typically using when we have two continuous variables that we've paired together. Okay, so it may look like a lot, but let's walk through this very gently and slowly, and we're going to be just fine. So one thing to notice, first of all, is that this is a fraction, okay? As you can see, there's a numerator up at the top here. That's called the numerator, of course, and then the denominator down here. So let's start with just that idea. What that means is that we're going to take whatever's in the top, whatever the numerator is, and we're going to then spread that out evenly over the bottom. A better way to think of that is what the R is a ratio of the numerator to the denominator. That's a really useful way to start thinking of this if you really want to get correlation and understanding correlation in your bloodstream, as it were. That's what one of my old professors used to call it. And so let's maintain that as thinking of the ratio of the numerator to the denominator. So first, let's start talking about the numerator and what that actually is. The numerator represents something called the covariance between our two variables. In other words, we have a variable called x, we have a variable called y, although we could name them whatever we want, and the numerator looks at just how their values seem to go together. Okay, so mathematically what I'm doing here, as you can see, is I'm calculating a mean for one of my variables, then I'm subtracting it from every one of the values that I have for that variable. This is a deviation score. That's exactly what it is, as you remember from our standard deviation. It's the same thing. Now what's interesting then is I'll find a deviation score, then I multiply it by the paired deviation score that I have with the other variable. Now that probably doesn't make a whole lot of sense, but here's essentially what I'm doing mathematically. Let me give you an example. Let's say that our x variable in this case is something like sleep duration, and our y variable is something like alertness the next day. Okay, sort of average alertness or something like that. So let's say that you've got somebody named Scott. Scott slept 2 hours, which deviates quite a bit from the average, and we'll say that the average is maybe 6 hours. Okay, so Scott then has a large number here. A relatively large number goes right here. But let's say he slept his alertness was relatively average. So then he's got a very small number here. In fact, let's call it 0. Let's say that he doesn't deviate from the average at all. So therefore, Scott's contribution here is going to be a big number times 0, which is 0. And therefore, Scott really doesn't contribute anything to the correlation because his values didn't seem to differ from the means together. Now let's imagine instead that Scott was highly alert the next day, but still had low sleep duration. Now you've got a deviation that's low, in other words, below the mean, and a deviation that's above the mean but high. Now you're going to get a large contribution, and it'll also end up being negative, right? Because a positive number multiplied by a negative number, it gives you a negative number. And if we sum up a whole bunch of negative numbers, we get a large negative number up here, which leads us to a negative correlation. As you can imagine, with a low value here and a high value here, those two things would be negatively correlated, right? Or let's imagine Scott had very low sleep and also very low alertness the next day, and so they would both deviate, but they would deviate in the same direction. A very low number times a very low number, we'll say they're both negative, actually gives you a positive number. A negative number times a negative number gives you a positive number, thus leading to a positively correlated R, or the two variables be positively correlated. So in other words, this numerator is all about where the values are similar to each other between the two variables. And this is for the paired observations. That's something very important, that it's not just the numbers generally, but actually the paired observations. It has to be Scott's value on X with Scott's value on Y. It can't just be Scott's value on X with Susie's value on Y or something like that. Okay, let me talk about this a little bit more in a new way. Let's imagine that you've got this Venn, well, I have a Venn diagram, we don't have to imagine it. But let's say that this variable is, the pink variable, or the salmon variable, is, let's say this is sleep, right? And let's call this one alertness, okay? Now listen, your alertness can vary quite a bit based on lots of things, right? And let's say that everything that causes your alertness to vary is wrapped up in this green circle. So that could be things like how much caffeine you had that day, the quality of your sleep, not even the duration necessarily, how disturbed your sleep was, for example. It could also be the kind of mood you're in, lots of things like that, how well you ate, you know, how much exercise you got. And let's say that that's all wrapped up in that. Now over here, if this is your sleep duration, that's also affected by a lot of things, right? That's affected by, you know, what kind of conversations you had as you were going to bed. What were the things you were thinking about before you went to bed? Your caffeine intake and all sorts of other things, right? So that's all wrapped up. Now what's interesting is that middle portion right here that I've circled in the red, that represents our covariation of the two variables. In other words, it's where your sleep duration and your alertness seem to potentially influence each other, but at least it's where we're accounting for where they change together in value, or how their values are similar to each other. The similarity between values might be a nice way to think about that. Okay, so that's the numerator. Let's now talk about the denominator. The denominator actually may seem a little familiar if you look closely and try not to get all lost in the trees here. So you've seen this portion before, especially when you have the mean and you subtract the mean from every value, then square those deviation scores and then sum those deviation scores. You recall that that comes from the computational formula for the standard deviation, right? It's just in the standard deviation formula, we also divided it by an n-1. We don't need to worry about that, however, for the moment. So we've taken that away because we don't actually need that. But this is exactly what it is the denominator is the standard deviation of the x value, the x variable, multiplied by the standard deviation of the y variable. Now that's really interesting, and you might say, well, why don't we have the n-1 business? Well, because we don't take the average up here. It's really not the standard deviation exactly, because we're not dividing it by the total number of observations we have. But that's fine because it doesn't change. They're the same number of observations in the numerator as we have in the denominator, and so that's just an additional step that actually doesn't add any value to it. So we can just remove that step entirely. But that's essentially what it is. So let's take an overall look now at the equation. So in words, you could really look at the standard deviation equation like this. It's just the covariance of the two variables in the numerator. Then you want to, in the denominator, it's the standard deviations of each other. So it's sort of the multiplied together standard deviations of both of the variables. And so what the R is, the R correlation is simply the ratio of the covariance to the standard deviation. You could also think of it sort of as like how much they change together, or how, not so much change, but how much the values seem to deviate similarly together, divided by how much variation there just is in the samples themselves, or in the variables themselves. And it's a very exquisite way to think about correlation. It's actually quite interesting the more you get to know it. Okay, so of course this calculation is a little, it's not necessarily super complex, but it takes a lot of steps. Luckily, we're not going to actually use this equation to calculate it out. I'll show you the calculating equation, the equation we'll use to calculate it right now. This is the computational formula for the correlation. It looks more complex, but it actually is easier to calculate itself. So as you can see right here, we already know all these symbols. We've seen all of this before if you've done the standard deviation with me. This, of course, n. In this case, the only difference is this is the number of paired observations of your variables. So in other words, if you had 10 people and you had an observation of each variable for that person, then n would equal 10, not 20. So it's not like you have 10 observations of variable x and 10 observations of variable y and multiply and add them together. It's the paired observations. And then everything else is exactly as you would think. So we're going to add that number in once we figure it out. I'll give you an example here in the next one. And this is the sum of squares, sum of the squared x values, sum of the squared y values over here multiplied by n. And this, of course, is simply the sum of the x values, sum of the y values. And you can see it's the same thing here. So no problem. This is going to be quite easy to calculate, and I'll show you how to do that next time. We'll go through an actual variable. The important point is that if you use the previous equation I showed you that just takes more steps, or this one, you should arrive at exactly the same number. They're mathematically equivalent, okay? However, we'll use this one because it just takes a few fewer steps, so it'll be very nice. Okay, we'll go through a problem and the actual calculations next time, and I will see you then.